Hello, I'm Angelos Pagonas, PhD candidate at the University of Pavia and member of the GECKO Doctoral Network. This video is based on my presentation at the technical workshop in Thessaloniki on May 2025, with a few adjustments to reduce overlap with my previous video, which covered mostly the introduction of the topic. Now the focus would be more on the progress of the research on immersed test geometric analysis and mass lumping for structural dynamics. I would like to start with a brief recap of what was established in the previous video. For a full introduction to the topic, you could watch that video first. It is available in our channel. First of all, IGA offers superior spectral approximation over standard C0 finite elements, thanks to its higher interelement continuity. And that makes it attractive for dynamics. The research is focused on immersed or trimmed methods, and specifically, we employ the finite cell method, where the physical domain is embedded in a structured grid and geometry is described through the integration process. This approach introduces a problem. Small cut elements, which are elements that are almost void and have small physical contribution, cause the maximum discrete eigenfrequency to diverge, making the critical time step in explicit dynamics impractically small. IGA combined with mass lumping was shown to bound the maximum eigenfrequency, allowing for larger time steps. But this stability benefit comes with a significant cost in accuracy for IGA. This slide shows the 1D setup used in the previous video for the bar example that also applies to the Bernoulli-Euler beam case we are examining in this presentation. The moving immersion boundary, or variable zeta as we call it, is the immersion parameter that controls how much of an element lies outside the physical domain. When zeta reaches the element boundary, the cut element disappears entirely and the behavior resets, similar to a boundary fitted case. And then increasing the immersion boundary more leads to a repeating behavior. As the moving immersion boundary increases, cut elements become smaller, and the maximum discrete eigenfrequency diverges, as we can see here. This has negative effects for the critical time step, as we already discussed in the previous slide. For a more detailed explanation of this setup, you can refer to the previous video. Moving to 2 dimensions, the construction is analogous. We now use bivariate tensor product splines. The same B-spline basis is applied in its spatial direction to discretize a square physical domain immersed in a structured grid, known also as the extended domain. The same divergence behavior of the maximum eigenfrequency with a consistent mass matrix is confirmed for all 4 cases in 1D and 2D and both second and fourth order equations. The beneficial effect of mass lumping, restricting the maximum eigenfrequency and consequently allowing for larger stable time steps, also applies across all these cases. Before looking at accuracy, here are the excitation scenarios used for the time domain studies. For each study, we use initial conditions that, after one period, are supposed to make the numerical solution return to the exact same position. So a perfect simulation would return to the exact same state. In this way, by reporting the global L2 displacement error between the numerical and initial solution, we have a metric for accuracy. Looking at accuracy results for the Bernoulli-Euler beam with single-mode excitation, the difference between consistent and lumped mass is evident. With the dashed lines, we can see the improvement of the critical time step after mass lumping. But apart from that, also mass lumping introduces a significantly larger error, looking now at the continuous lines maybe, compared to the consistent mass case here, confirming that the stability benefit comes with a real cost for accuracy. This is the same conclusion we reached for the bar in the previous video, now extended to a fourth order problem. A similar phenomenon emerges for the membrane problem also. Consistent mass preserves accuracy and lumped mass degrades it significantly. This pattern is similar across all cases, covering both 1D and 2D and both second and fourth order PDEs. The trade-off is a fundamental consequence of row-sum lumping in the immersed IJ setting, and this is regardless of the problem type. One alternative to mass lumping could be stabilization. Artificial mass and stiffness contributions are introduced in the elements lying in the fictitious domain, and this is basically stabilization. This bounds the maximum eigenfrequency and recovers stable time steps. It is important to emphasize that accuracy could be improved, but also comes at a significantly higher computational cost, and this we have to consider depending on the application. Another factor worth mentioning is that based on studies across several initial conditions, we noticed that the accuracy obtained is sensitive to the choice of the stabilization parameter. So tuning that parameter may not be that simple. Now, so far we worked with controlled setups, the 1D cases, and the axis-aligned 2D immersed square inside another square, where a single parameter zeta was sufficient to predict where spurious eigenfrequencies would appear. In those cases, the tiny mass of a cut element alone was a sufficient indicator of problematic areas. To move towards something more realistic, we now consider a rotated square, a deliberate step towards a more arbitrary geometry. The immersed boundary trims the structured grid at an angle. This requires a quad-tree approach for integration near the boundary, as shown here. With rotation, more variables comes into play. The angle, the quad-tree levels, and not just the zeta variable we had before. And as we're about to see, the tiny mass of a cut element is no longer sufficient to identify where problems will appear. So to isolate exactly what changes, we construct a control comparison. The two configurations have same geometry, polynomial degree, number of elements, quad-tree levels, and by construction, the same very small cut element mass in the corners of the physical domain. The only difference is the local environment of the small cut elements, meaning their neighboring elements and which are more full or mostly void. While both configurations have the same small mass by construction in the small elements of interest, the maximum eigenfrequency differs by 6 orders of magnitude. The zoomed views, as we can see here, could give us some hints about the why. In the right setup, looking closely at the corner, a tiny cut element can be surrounded mostly by void elements, meaning there is almost no physical mass available in the surrounding region to compensate. This demonstrates clearly that using mass alone as a local indicator to identify problematic areas is misleading. And what we need is an indicator that also accounts for the local environment of each element, basically how it connects to its physical and fictitious neighboring elements. Based on what we've seen, the natural next step is to move beyond observing these effects and work towards understanding the underlying mechanisms that drive them. So a productive way to approach this is to first decompose the problem, meaning treating immersion and mass lumping as independent effects and studying each one separately before looking at their interaction. This should help isolate the root causes rather than just reporting the combined outcome. And then with that understanding in place, revisit again the broader picture of what happens and when both effects interact. And finally, towards handling more complex geometries, to develop a reliable local indicator for problematic areas that is able to go beyond just the element mass and to account for the local environment as we just demonstrated. With that, I would like to finish my presentation and thank you for your attention.